after 7:30.
Okay.
Right. Good evening, everyone, and welcome to another CAS webinar. Tonight, we have space news from Roy Bryce. Then our main speaker for this evening is Paul Hearn of the BAA Radio Astronomy section. He is the director, whose presentation is entitled Radio Astronomy, So Much from So Little. Our next webinar is on the 25th of April, when our speaker will be Dr. Luke Daly, whose presentation is entitled, Where Did Earth's Oceans Come From? Now it's over to Roy for space news.
Thanks, Amanda. Just the usual, I bring up the screen. Somebody else just joining. That was good timing. So I usually lose the screen. Okay, can you all see the slide screen okay?
Yes.
Yes.
Excellent.
Yes.
Okay. And here we go. There's a lot of major questions that researchers initially figured that the James Webb Telescope would answer once it launched in the early 2010s. But when that massive space telescope got delayed and delayed again, researchers creatively came up with other ways to get the data they needed. Through a combination of computer models and creative telescope use, the astronomy community built up a picture of massive objects coming together, galaxies building up, and stars forming throughout the mix. And that star forming was just a healthy run-of-the-mill, slow and steady, regular rate. But that understanding came more from computer modeling than from observational data. Using new data coming to us through the combined efforts of the Hubble Space Telescope and the utilization of galaxy clusters as gravitational lenses, researchers have found ways to start to image distant galaxies. And thanks to the time it takes light to reach us, we're seeing galaxies as they appeared early in the universe. A new paper in the Astrophysical Journal points out that 60 to 90% of these galaxies were experiencing extremely high levels of star formation, consistent with them being star-bursting galaxies. This work was led by Pierluigi Rinaldi. In a non-star-bursting galaxy, like our Milky Way, we see pockets of star formation associated with giant molecular clouds, collapsing into stars and forming star clusters. These galaxies may form one to a few stars a year. And these pockets of star formation are generally triggered by regular events like supernova, collisions between clouds, and other minor shocks. In a star-bursting system, massive events such as the collision between two systems can cause the bulk of the gas and the dust in the system to engage in star formation. These kinds of galaxy-wide events generally last 10 to 100 million years, and galaxies can undergo multiple bursts of star formation over time. Current models of the evolution of the early universe don't predict a lot of starburst behavior, but the epic combination of the Hubble, Spitzer Space Telescope, and the ground-based Very Large Telescope was able to discover 20,000 different galaxies. This group found that 20 to 40% of these star-forming galaxies were undergoing starbursts and were forming 60 to 90% of new stars. This is compared to today's rate of about 10% of stars coming from starburst galaxies. According to Rinaldi, even the latest and most sophisticated models of galaxy formation hadn't predicted this. It seems likely that the physical processes occur at too small a scale for the models to account for it. Along with discovering star-bursting galaxies with Hubble and Spitzer, researchers are finding actively feeding black holes with the Chandra X-ray Observatory. Galaxy J11402629, or the Spiderweb galaxy, sits at the center of a forming galaxy cluster. Chandra peered into this region for 8 days and discovered 14 actively feeding galaxies in the region, which is just 11.3 million light years across. These systems are coming together at the same point in the universe's history as the starburst galaxies we just looked at. Just as starbursts can be caused through collisions, dust and gas can be sent cascading into the center of galaxies, where they can feed black holes. We don't know if, oh, hang on, let's admit David Ramshaw, just a wee second. Yeah.
Roy, I'll need to leave the meeting and come back in again. I need to send Lynn the link for the meeting, and I can't get it sent on my iPad. I can't.
Okay, you come out and I'll let you back in again then. Yeah,
right,
sure.
okay.
So carrying on with this. We don't know if collisions are triggering any of these systems for sure, but it is intriguing to think about. To get to the bottom of why so many galaxies are so active, the team will be pouring through old Hubble data to see what can be seen. They'll also be using Chandra to observe additional galaxy clusters in the process of forming. These newly discovered active black holes are described in a new paper in Astronomy and Astrophysics, led by Paolo Tosi. Because I let somebody in, I've just got to go down here and get the screen back. Here we go. While the star-bursting active galaxies we've discussed so far are too far away to be seen in any amount of detail, they do have siblings in our own modern universe that gives us a taste of what these larger populations may have looked like. At the start of April, the teams at NASA and ESA provided us with a new stunning Hubble image of the active galaxy NGC 7172. This system has an incredibly bright core dominated by a disk of material that is spiraling towards the black hole's event horizon. This disk is so dense that it's able to generate its own light and even undergo some nuclear reactions. Dust that's a safe distance from that hungry supermassive black hole is backlit in this image, and the star formation can be seen glowing blue along the galaxy's edges. Imagine living at a time when this kind of stunning system is the norm and not the exception. That brighter time is what we hope maybe the JWST will show us in great detail. Here's Alice Amanda coming back in. Hopefully you're back, Alice Amanda, because I'm about to start playing a video. Oh, you are, good, okay. So, here's an item that I thought was offered an interesting new insight. I've been sort of backing off playing videos for a while, but I did like this one. It goes on a wee bit, but as I say, I thought it was interesting. So hopefully we'll let the professionals explain what's going on.
Using data from the European Space Agency's Gaia mission, astronomers have shown that part of the Milky Way, known as the thick disk, actually began forming some 13 billion years ago. That's around 2 billion years earlier than previously thought, and just 800 million years after the Big Bang of creation. The findings, reported in the journal Nature, are based on positional data from Gaia's early Data Release 3 dataset, combined with measurements of the chemical composition and consequently the ages of 250,000 stars given by LMOST, the Large Sky Area Multi-Object Fiber Spectroscopic Telescope. The authors, who are from the Max Planck Institute, looked at stars known as subgiants. These are stars no longer on the main sequence, so they're no longer burning hydrogen into helium in their cores. Instead, these stars have started the process of shell burning, that is, converting helium to heavier elements in their core and burning a shell of hydrogen into helium around the outside of the core. Now, this subgiant phase is relatively brief in the evolutionary history of a star. It therefore permits the star's age to be determined with a great degree of accuracy, but it's still a tricky calculation. Under any circumstances, the age of a star is one of the most difficult parameters to determine. It can't be measured directly. Instead, it needs to be inferred by comparing a star's characteristics with computer models of stellar evolution. The compositional data then helps with this. It works like this. The universe was born 13.8 billion years ago with almost nothing but hydrogen and helium. Tiny trace amounts of lithium and beryllium, sure, but primarily it was a hydrogen and helium universe. 3/4 hydrogen, 1/4 helium. All the heavier elements, including the oxygen you breathe, the carbon you're composed of, and even the iron in your blood, was all made inside stars, either during their lives or when the stars died. These elements, which astronomers refer to as metals, were then incorporated into future generations of stars. So, stars which were formed early in the universe's history have fewer metals, and therefore lower metallicity, than stars which were formed more recently. And LaMost provides data on this metallicity. And together, the brightness and the metallicity allows astronomers to determine a star's age. Our galaxy, the Milky Way, is made of numerous different components. Now, broadly speaking, these can be split into the halo and the disk. The halo is the spherical region surrounding the disk, and it's traditionally been thought of as the oldest component of the galaxy. The disk, which is where the galaxy's spiral arms are located, is composed of two parts. There's a thin disk, and superimposed on that is a thick disk. The thin disk contains most of the stars that we can see in the night sky, and our sun is a member of this thin disk. The thick disk is more than double the height of the thin disk, hence its name, but it has a smaller radius, and it contains only a few percent of the Milky Way stars in the solar neighborhood. By identifying subgiant stars in these different regions, the study's authors were able to build a timeline of the Milky Way's formation. But what they found came as a real surprise. The stellar ages clearly revealed that the formation of the Milky Way fell into two very distinct phases. In the first phase, which started some 800 million years after the Big Bang, the thick disk began forming stars. The inner parts of the galactic halo may also have begun coming together around this time. But the process rapidly accelerated to completion about 2 million years later, when a dwarf galaxy, which we call the Gaia Sausage Enceladus, merged into the Milky Way. It filled the halo with stars. And as the new work shows, it also triggered the nascent thick disk to form the majority of its stars. The thin disk of stars, which includes our sun, was formed later during a subsequent second phase of galaxy formation, possibly when the Sagittarius dwarf galaxy slammed through the disk of the Milky Way on one of its earlier encounters with our galaxy. The analysis also shows that after the star-forming burst triggered by the merger with Gaia Sausage Enceladus, the thick disk continued to form stars until the gas was mostly used up roughly 7 billion years ago. During this time, as stars were born and died and their contents spread throughout the galaxy, the metallicity in the thick disk grew by a factor of 10. But remarkably, the authors see a very tight stellar age metallicity relationship. And this indicates that throughout this period, the gas forming the stars was well mixed right across the entire disk. And that suggested the Milky Way's disk regions must have been formed from very turbulent gas that was effectively spreading metals far and wide through the galaxy. The earlier formation of the thick disk points to a different picture of our galaxy's early history. Since the discovery of the ancient merger with Gaia Sausage Enceladus in 2018, astronomers had already suspected that the Milky Way was there long before the halo formed, but they didn't have a clear picture as to what the galaxy looked like. The Gaia spacecraft will deliver its full third data release on June the 13th. This catalog will include spectra and derived information like ages and metallicity. And that will allow astronomers to piece together the history of the Milky Way in even more unprecedented detail. This report from ESA TV.
Rotating slowly 1.5 million kilometers from Earth, Gaia is scanning the entire Milky Way. Since 2014, the mission has been mapping the distance, position, and movement of 1.7 billion stars to reveal our galaxy as never before.
The scientific impact of the mission already is immense. We see 3-4 papers appearing per day. We're touching virtually every area of astrophysics, from very fundamental predictions of 50 years ago to new things that you see and the dynamics and the history of our own galaxy.
Capturing 70 measurements at every star, Gaia produces vast amounts of data. At a meeting in Groningen in the Netherlands, scientists have been discussing the challenge of processing and visualizing this information.
Gaia is probably one of humanity's greatest missions, one of the greatest catalogs of data that has currently existed for humans to go through. And it's almost impossible to give you all of the ways in which Gaia is impacting astrophysics.
Earthbound observatories provide a snapshot of celestial objects in the night sky. But by measuring how the stars are moving and visualizing that data, astrophysicists are using Gaia to trace the history and evolution of the galaxy. They've discovered, for instance, that stars born together in star-forming factories move in clusters or families throughout most of their lives.
It is mind-blowing. I can't believe we can do this. I could never have dreamed that we could pull away from our position on the Earth and actually see the structure of these kinds of associations. And then you can run time forward and see exactly how they're moving. You can compare and contrast how they're all moving differently. And I think it's a story of vast proportions in our understanding of how stars form and evolve.
Other science teams have used Gaia data to confirm today's Milky Way is formed from giant galactic mergers.
So most of the stars in the Milky Way rotate like the sun in a clockwise sense. So for example, what we discovered is a very large group of stars that are going the other way around. And so that's already very suspicious. And it tells you kind of that these stars were formed elsewhere, being such a large group. And it's also a very old star. So that was already the first hint that actually one component of the galaxy is probably made up from stars born somewhere else.
Across Europe, hundreds of people work on the Gaia mission, ensuring the data is accessible to everyone.
Gaia is currently in an extension of the original 5-year mission. What we do is we gather more data, we get better statistics, and then we can derive more precise results.
Galaxies come in all shapes and sizes, and while several 100 billion galaxies are estimated to be in our universe, only one of them is home to Earth. Our planet and its sun lies in one of the Milky Way's spiral arms, but while special to us, our sun is just one of around 100 billion other stars in the galaxy. So in order to better understand the Milky Way, its past and its future, the Gaia spacecraft has been surveying the skies since 2014, and it will make up to 70 observations on average for each star over the 5-year mission. The first data release in 2016 charted 1 billion stars, but only included the distance and motions for 2 million. The second release has now updated this to an extraordinary 1.7 billion, and with greater accuracy, including the distance and motions for nearly all the surveyed stars. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the color, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparchus, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along Earth's orbit around the sun and separating it from the star's true motion through the galaxy. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids, and far away, it measured the positions of distant quasars to create a new cosmic reference system. But for astronomers across the world, the best is yet to come.
The essential thing of the Gaia mission is that the surprises will come later because we make the catalog, and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
Gaia is not only mapping the stars, it's giving us a new sense of our place in the universe.
Sorry if that was a bit long, but I really am just astonished at the sort of detail that's coming out of Gaia. It's just been an amazing mission. Everybody goes on it about Hubble because you get these beautiful photographs, but the science that's coming out of Gaia is astonishing. Anyway, Now for an amazing photo taken from orbit by NASA's HiRISE orbiter. HiRISE frequently monitors surface assets of current and past spacecraft mission to Mars. This includes the latest NASA lander sent to Mars with the Perseverance rover that landed on the 18th of February 2021 in Jezero crater. The 3 by 2.7 meter sized rover is sitting on the fractured bedrock of what mission scientists are calling the Mars Formation, thought to be of igneous origin. The primary science target is the deltaic deposit thought to have formed billions of years ago from sediment that an ancient river once carried, which is still several kilometers to the north. HiRISE is likely to image Perseverance again during its long traverse to get there. Also in this photo, 200 meters to the west, is the Ingenuity helicopter that's now completed 23 successful flights in Jezero since it was deployed. Last weekend, on April the 3rd, NASA's Exploration Ground Systems Office was supposed to conduct the wet dress rehearsal for the Artemis 1 Space Launch System rocket. This would have been a complete countdown test, doing all of the same procedures as a real launch, going right up to the moment of ignition, 10 seconds before launch. I was hoping to report on this milestone for you, but instead you're going to get a lesson on how developing and testing a new rocket isn't easy. After rollout 2 weeks ago on March the 18th, engineers got the rocket hooked up to the pad systems and began to turn it on. The wet dress rehearsal was scheduled to end on April the 3rd, with the countdown actually starting 45 hours before that. Everything went smoothly, even as a lightning strike near the pad hit one of the lightning towers as intended, and not the rocket or its mobile launcher. That is until about T-9 hours, when it came time to start filling the different stages with the very cold liquid oxygen and liquid hydrogen propellants. However, this first attempt to load propellants was scrubbed because fans that keep toxic gases out of the mobile launcher weren't functioning, so technicians couldn't do the job safely. The launch team reset for the next day, which was April the 4th. This time, both the weather and the mobile launcher cooperated, and the EGS started loading propellant into the SLS rocket. First, the liquid oxygen into the core stage. Loading stopped for several hours because of a temperature limit. After analysis, the teams resumed. Then another issue came up, this time with a gaseous hydrogen vent valve on the core stage, specifically the ground system that controls it. This valve directs boiled off hydrogen out of the core so that it doesn't rupture it. The team didn't have time to solve this issue before the shift ended, so the launch director just called for another scrub. What does this tell us? Well, rockets aren't easy. They're massive, immensely complicated machines. Even if they've worked once or a few times, that's not a guarantee they're going to continue to work, especially if there's new systems involved that work separately. EGS are going to try again tomorrow, and hopefully they'll get the wet dress rehearsal done. So, as always, thanks very much to the Cosmic Quest and Universe Today people for the podcasts and the newsletter that give me the up-to-date information that I use to compile the Space News presentation. And that's the Space News for tonight.
Right, thank you very much for that. It was amazing the amount of information that Gaia's provided.
Yeah.
The number of stars, the 1.6 billion, that is really fantastic. It's fantastic stuff that's coming out of that.
The next release of Gaia data is due on the 13th of June, I think.
Yeah,
they're having a race with the James Webb Space Telescope first announcement. So they're intending to get the Gaia data release 3 out just before James Webb Space Telescope takes over all the news, apparently.
I see.
Right.
A wee bit of international non-cooperation. Certainly.
It's all about politics and money, isn't it?
It is.
Aye, true. Aye, it seems to be.
Presumably takes months to work through anyway. So.
Aye.
It's only getting, all it will do is put it on the computer. You've then got to start looking at it and spend millions of years downloading it.
Aye. That was fascinating. That video, really interesting. Aye. Right. Paul Hearn has spent 40 years working in the realm of electron microscopy, and he says he now finds himself 30 order magnitude in the opposite direction. He said he is not a scientist, but a retired engineer. He only started studying radio astronomy in 2018 and soon discovered that instruments could be built for RA observation and provide so much from so little. Paul's focus tonight will be on what the intended researcher can do at home. So let's give Paul our usual Kaz warm welcome.
Thank you very much. And thank you, Roy, for the news. That was just great. Right, I think I've shared my screen. Can you?
Yep,
And you can hear me okay?
we can.
Yes.
Right, we've established comms. Right, good evening, and thank you for inviting me. Right, yeah, as Alice Amanda said, I'm not a scientist, and I haven't been doing astronomy for very long. But it hit lots of boxes when I retired, and I was just astonished as to how much could be achieved from just so little. And so tonight we'll be looking at some of the techniques that the independent researcher, the amateur astronomer, can do. And all the things I'm talking about are done by folk within the radio astronomy the radio astronomy section. So we're going to have a brief journey through the electromagnetic spectrum, and we're going to have a look to see what radio waves can inform us about the universe in which we find ourselves. Oh, what's happened here? Oh, I see. I hit end instead. I wonder if I can go back. Yeah. Wasn't expecting that. Right. So it's more of a chaotic leaping through the electromagnetic spectrum, if truth be told. But I hope by the end of the evening, you'll have a feel for the sort of observations that amateur radio astronomers can do, sitting in their sheds or in their labs. But I want to start by something I discovered relatively recently. I'm sure you'll all be aware of these beautiful cave drawings in central France, and this is just one, but there are antelopes which are anatomically correct in their leaping, and these were drawn 16,500 years ago. And I'd seen these drawings before, and our story tonight starts at this point because it was pointed out to me that with very little imagination, we can see that, now I need a laser pointer, so just be careful. Laser pointer, there we go. Can you see that?
Get it?
That's at the top here, we can see the, as I say, without too much imagination, the constellation of Pleiades, and I think with a bit more imagination, you might see Hades here, and then Orion's Belt possibly. But it was pointed out to me that maybe over the course of the drawing, this was in fact a planet that changed its position. So maybe we've got a recording here of some time domain astronomical observations of a planet. But throughout the history of man, we've been fascinated by the night sky. I've done very little optical observation, and I'm sure you guys spend a great deal of time staring at the night sky and just being absorbed by the complexity and the wonder and beauty and privilege of being a part of such a system. And I'm sure the ancients had the same kind of emotions as they were staring up at the sky. For no particular reason other than that it's a beautiful image, and it's a composite of optical and infrared. And in my mind, infrared is verging on the radio astronomy section, on the radio astronomy part of the electromagnetic spectrum. And this is, a fantastic image. I'm sure you've seen it before, but it's just an excuse to remind us of the beauty of the universe, the Orion Nebula, and the Veil Nebula as well. Astonishing images, and has already been noted. Later in the year we're going to get some very interesting and spectacular images from James Webb. Again, we've all seen this spectacular image of galaxy M87 from a few years ago, where the Event Horizon team, 100 scientists with, I think, $10 million were able to produce this image. And we can see the Doppler shift as the whole structure is rotating there. No talk on radio astronomy would be complete without this photograph. And if you've ever had anybody talking to you before on radio astronomy, I'm sure somewhere at the beginning, this image of Karl Jansky would be shown. I don't think there are many pictures, and I've seen this one lots of times. I make no apologies for including it. It's 1937, the beginning of radio astronomy. And Karl was working for Bell Telecoms at the time. I'm not sure what they were called then, Bell Labs now. And he was concerned with noise on the signal and deduced ultimately that it was of a cosmic origin. And this was the birth of radio astronomy. Radio astronomy has informed some fantastic deductions about the cosmos. And in the 60s, I remember, and it was what motivated me into astronomy, even though I left it for 50 years or so because I was busy doing other stuff. But in the 60s, I used to avidly watch Horizon as a student and as a teenager. And I remember the debate, Big Bang or constant state. And it was radio astronomy informed that. And this image was only produced in 2013. But the cosmic microwave background was just ubiquitous and not with higher reference when we overlay the stars and galaxies, etc. And it was this that is evidence of what we now understand as the Big Bang theory that's generally accepted in cosmology. Right. I'm going to have a quick zip through some different wavelengths of what we can observe. And the example I've chosen is a Crab Nebula. And the first image there at the top, my laser point, yes, laser point still working. The X-ray image at 0.1 nanometer in wavelength. And it's a map of how energetic, how hot the electrons are there. And then going from 0.1 nanometers to 10 to 400 nanometers. So we're just below where you would be familiar in the optical range, coming up to 400 nanometers. And it's the ultraviolet region. And it's showing, again, you could regard it as a map of electrons with a better cooler, less energetic. And then an image here that is something that we would all be familiar with in the range of 400, 700 or so nanometers. And then like pure radio astronomy, gives a completely different kind of image. And remember, each of these images are looking at the same object in the sky. And we're seeing here at the bottom right the free electrons interacting with the magnetic field. Radio signals are weak. Professionals and amateurs alike struggle with the signal compared to the background noise. And I always thought broadcast signals were weak, judging by the gain in systems for television reception and radio reception. But we can see on this chart here that the broadcast signals are nominally 10 to the minus 13 watts per square meter hertz. And moving into radio astronomy and pulsars, 10 to the minus 25 watts per square meter. The signals that we get are just astonishingly small. Okay, a bit of O-level physics, just as a revision, just to give some context of what we've just been looking at and where we're going later on. So on the left-hand side here, we've got wavelengths of about 0.1 of a nanometer, where we're seeing gamma rays, X-rays, moving up to the ultraviolet. And then the visible spectrum is very small compared to the rest of it. And remember, the horizontal line here is logarithmic, so it's actually smaller than it appears here. Fortunately for us, the atmosphere protects us from the gamma radiation, X-rays, ultraviolet, etc. It's all blocked, and we don't experience it at ground level here. We've then got the infrared through here to most of the infrared spectrum is in fact absorbed by the atmosphere, so it's observed from space. And James Webb has worked in that region, of course, as you all know better than me probably. We've then got a window here where from about 5 centimeters in wavelengths up to just beyond 10 meters, we can have direct observation of those wavelengths with ground-based systems. And then the very long wavelengths are again blocked by the atmosphere, and from about 10 meters to 100 kilometers. Right, I just include this for completeness, but amateurs with ground-based systems can't record X-ray data. However, the GEOS satellite data is all available online and can be readily downloaded. NASA make all this data freely available, being a publicly funded body. And I just grabbed these spectra from at random back. Yeah, it happens to be last November. So the top one is a not very interesting day, and then the lower, they're not spectra, are they? But the lower data, November the 9th at 4 o'clock, we've got an X-ray event here, and we'll come back to these events in a moment. Okay, during periods of activity, the sun produces massive electromagnetic releases across the whole spectrum, from gamma rays, X-rays, radio waves, free protons, magnetic field disturbance, all of this exciting stuff as the energy is just released as a mass ejection from the sun. And one thing I want to do at some point is set up a solar telescope to observe some of these things, some of these events directly. But much of this is readily observed by the independent researcher. And you'll notice in this presentation, I interchange independent observer with amateur, because amateur has some connotations that are not particularly helpful. And many of the amateurs in our group are equally competent with professionals. Some of our amateurs teach MSc Astrophysics and Radio Astronomy where they are, and some of them have collaborations with academics. So that's the reason I interchange the two terms. So much of this solar phenomena that I've just quickly described can be observed by independent researchers, and we're going to look at how in a moment. We will be aware of the national or international register of risk because of the pandemic we've just been through. But a few years ago, solar mass ejections were added to the risk, the national risk register, because they can cause serious problems. NASA monitor this activity because they don't want their astronauts outside the spaceship at the time. Crew and airline passengers having in any case an increased radiation load when they're flying. And if any of you have had to work in an environment where you carry a film badge, I'm sure your health physics people have said, don't put it in the, don't wear it on a flight or put it through the security at the airports. Of course, these phenomena produce beautiful atmospheric effects of like the aurora, and induced currents in power systems can cause problems, as well as satellites. Sometimes they have to be shut down so that they're not damaged by solar flares. I just had a look at this today because any of you that have been following solar activity would be well aware that over the last week or so, there's been some really violent outbursts. However, today is a rest day, and you can see there's absolutely nothing happening. Whenever I dip into this and have a look, there's usually something. I don't think I've ever seen a completely clean image like that. But anyway, that was today at 1:30. Okay, so what can the researcher do? And I've tried to do this in order of difficulty. So the first thing is meteor observation by forward radio scatter. We're aware, and maybe some of you have even do some meteor observation with visible light, just having a look and watching them flying across the sky. I know that I have, but it's a great technique for new members to get involved with, because it's quite a simple thing to do, radio observation of meteors. Sudden ionospheric disturbance using very low frequency radio reflection. And we'll unpack these a bit more in a moment. Geomagnetic observation. I've got a magnetometer on the desk just a meter away from me that's logging 24/7. Solar natural radio spectrometry, a bit more difficult to do, but can be very rewarding if you can achieve that. And we'll look at the problems with that in a moment. Cosmic radiation detection by muon counting. This is very exciting and something that is becoming more easy with greater sensitivity than previously. And again, we'll have a look at that in a moment. If you've got a bigger budget and a large garden, then hydrogen line observation with a dish is possible. Pulsar observation if you're good with electronics, but more importantly, signal processing. And I'll show you some results in a moment from Peter East, whose software, I mean, he's an amateur radio astronomer, but his software is used by professionals for deconvoluting pulsars out of noise. And fast radio bursts. This is quite a new field and not that easy to do unless you've got some budget and a lot of space. But we do have a group within the section that are doing work with fast radio bursts. So the topics in yellow we're going to unpack and have a look at in a bit more detail. This is my own lab, so we've got muon counting, always code. And the thing that draws people into radio astronomy very often is the ability of to write code, play around with code, electronics, solving lines, etc. meteor monitoring, geomagnetism, as I mentioned a moment ago, sudden ionospheric disturbance monitoring, and again, always code. I went into radio astronomy when I retired because I wanted to get back to my roots, which were Fortran 4 in the deep past and working with electronic hardware, which I moved away from in the course of my career. Okay, for scatter meteor detection. So what's happening here? So a meteor will come into the upper atmosphere, and with its interaction with the molecules in the upper atmosphere, it will ionize. So we have charged particles following in a tail behind the meteor, and these charged particles are positive ions and electrons. And this vapor trail, this plasma trail, will reflect radio waves. And very conveniently, there are a number of transmitters that can be used for this. And in the UK, many observers use a transmitter in Dijon that the French military established many years ago for their air defense system. And it's at 140 megahertz. And with the right receiver, we can tune to that radio. And when there's a meteor coming across between it and us, then we get a ping, and we can see the meteor. Oh, there's a photo of the array in France. That's the antenna in my garden. A very simple Yagi antenna, just 3 elements used for meteor detection. And the electronics are even simpler these days because these dongles are sold. Price on this one is £100, but £10 would be enough. And these are sold primarily for decoding digital TV and radio, so you can watch on your laptops. You may even have one yourself. But for radio astronomy, and other elements in radio astronomy as well, they can be very useful and provide an analog to digital conversion, taking the radio signal in at one end and squirting it through the serial port at the other end. And the kind of data we have, I just grabbed this one at random. It's quite typical. If you are meteor counting, in other words, how many events in an hour, and that's plotted where there's 24 little squares for a day, and going across there's 28 or 31 columns where the color will represent the number of counts, meteor counts in the in that hour. But that's just counting. I'll come back to that slide in a minute. This is a bit out of, I think I could have done this better. But if we look at the actual radio signature, then we've got a head echo, and the vertical scale is frequency, and time is on the horizontal scale. And these are typically minute max, I would say. I haven't done a great deal, but it's that kind of magnitude. And the observers that are doing more than just counting meteors have a look. We can look at the characteristics of these of the first echo, the head echo, and come to some conclusions about the physics of the upper atmosphere at that point in time. We can have a look at the Doppler shift and come to some conclusion as to where the meteor is in terms of distance from us. Data can be correlated with other observers to try to get a lat and long from the event. And there are a number of observers that have all all sky cameras, although I'm sure going forward there'll be a lot of noise from Elon Musk's satellite. But here we can see some meteor events. I don't know how, I think this might have been through one night of a good period, about 8 hours. But to correlate this data with radio data is something that people are working on. And I said that most observers in the UK use the transmitter in Dijon. There's one in Belgium as well, but neither of them are very well placed for the best results in this country. And Dijon has particular problems because of the characteristics of the radio transmission. It scans and pulses for reasons that escape me, but probably the air defense people in France understand very well. And but it's not great if you're trying to come to conclusions about the science of head echoes and coming to want to study upper atmospheric physics based on radio forward scatter from meteors. Okay, so that's meteors. Now the next one in our list of things you can do in a shed at home is sudden ionospheric disturbance detection using very low radio reflection. Okay, so what's happening here? Very low frequency radio, it's between 15 and 25 kilohertz. So it's very low. I mean, it's only just above the of what you can hear. And these transmitters are maintained by governments that have submarines, so they can talk to their submarines without the submarine having to surface. However, for sudden ionospheric disturbance that results from solar activity, those observations are great at these frequencies because the ionosphere responds very quickly to changes in solar X-ray and UV emissions that are associated with solar flares. And those signals can be very easily processed with quite a simple amplifier and an even simpler loop. This is a kit that's provided by the UK Radio Astronomy Association, and you plug your aerial in one end and a computer in at the other, and gets results a bit like this. So this is a 24-hour period, and at dawn, the ionosphere is settling down, new ionization is occurring as the sun comes over the horizon, and then we get a settled period through the day. And these three traces are from three different transmitters. They'll all be at different frequencies. And then as the sun sets, recombination in the upper atmosphere will occur, and things settle down for the night. Now, if we have an event during the day and the lower trace shows an event, then we get this very characteristic change, very fast change in the amplitude, and then a recovery. And that can be negative going or positive going, depending on the phase of the signal. The incoming signal to the receiver will either be reflected from the ionosphere, or it'll be a ground wave. And if you're monitoring both, or you're lucky enough to be able to monitor more than one station, then the likelihood is you'll get an out of phase signal and will have both characteristics. So we can pinpoint here the time at the CME disturbance impinges with the upper atmosphere. And here's a rather pretty one. And we're monitoring 6 different radio frequencies here, and we can see they all have a slightly different characteristic in the curve, and deductions can be made from that again about radio propagation from the atmosphere. Okay, geomagnetic observation. I just love these animations from NASA. So we've got a solar event here, and we can see that on the side facing the facing the sun, the Earth's magnetic field has become distorted and compressed, and then on this side away from the sun, the magnetic field from the Earth is elongated. So this violent event of solar activity causes an equally violent change to the Earth's magnetic field. I don't know why I include that. It doesn't inform the debate very much. It's a pretty picture, and I'm just wondering what's going to happen to this poor satellite sat here. But anyway, you get the idea. Required is the magnetometer, and as I said earlier, I've got one just sitting on the bench over there, taking data 24/7, and it's quite a simple board. There's a little bit of electronics and an analog output where the analog voltage is just a couple of volts, and that will change as the Earth's magnetic field changes. And so we can plot that on a computer. I take this into a Raspberry Pi, but it doesn't have to be. And on the left-hand side here is data from the Swedish Institute of Physics, and it's the same day, which was in April last year. Don't know why I chose that date, but there we go. So I often, if I'm recording data and having a look, I try to look at a professional lab's data just to see what they're observing compared to what I'm picking up. And we can see here in the early hours, there's an event, and the time constant for the data between the two data sets is quite different. I've got some greater integration on my data here, but we can see there's an event here just before 2 a.m. and in Sweden, they've recorded an event as well at the same time. And then later in the day, 9 and 10, there's quite a lot happening here in terms of changes to the magnetic environment of the planet. And again, here we can see that my own magnetometer has picked up changes to the magnetic environment. And I include this one. Yeah, I just had this data published in the Radio Sky Notes from February last year. Okay, natural radio spectroscopy. I'm going to go through this fairly quickly because it's something that people can do. If you're in a perfect location, you can get some very spectacular results. But as I said earlier, one of the things that happens with a solar flare, these violent events, as well as X-rays and extreme ultraviolet, etc., we get natural radio bursts, and we can run a spectrometer 24/7, just scanning the range and see the we can pick up the changes in the natural radio. And all we need for this is a high gain TV aerial pointing at the sun, and then it has a very large aperture. So from midday, probably plus and minus 4, 5, or 6 hours, you'll be in a position to take radio spectra. And all that's required in terms of the hardware is a receiver and a laptop, and it scans between 45 and 870 megahertz. And the real problem here, the problem that I found, and that many people do find, is that in that band, the 45 to 800 megahertz, is the broadcast TV, digital TV channels, and there are quite a lot in there. So one has to set up the solar radio scanner very carefully so that it skips those channels and is only looking at the little bits of the spectrum that don't carry interference from digital TV. And then the sort of results we can get are this. So this is frequency running from 20 to 60 megahertz in this instance at the top, and then time time at the bottom, and they're quite fast to burst. We can see that this recording started at 11:56 and went on to 11:57. So, quite fast. But I was at a conference just last week where this data was presented with exactly the same hardware that I showed you earlier. And this was just at the end of March. And at the end of March was also a very active time for solar activity. And we can see here there was some pretty spectacular radio bursts. To interpret what this means in terms of the heliophysics, then that's really complicated. And what I would say is it's beyond the scope of this presentation. But in reality, it's beyond the scope of my understanding. Okay, yeah, some more solar radio bursts. I said I was going to skip through quickly. Right, cosmic radiation detection by muon counting. This is really interesting. Where does the cosmic radiation come from? Well, again, there's a constant background, and massive events, cosmic radiation events, can occur from exploding supernova and other such energetic events in the solar system. And this one I found, yeah, was in 87. And again, another NASA animation, but along with all the other exciting stuff that happens with a solar event, we get cosmic radiation, very high energy particles, predominantly free protons emitted from the sun. And these can be detected. And this is particularly interesting because many amateur radio astronomers, as I've mentioned earlier, monitor solar activity through radio propagation or geomagnetic effects, and this is another data stream where correlation can be applied, and we can do some time domain stuff as well between these different observational techniques. So just a little bit of physics, probably a bit of A-level physics this time. Not very much, just a couple of slides. But a free proton will enter the upper atmosphere, and there'll be nuclear reactions. And these nuclear reactions produce pions and neutrinos, which we're probably quite familiar with from the science documentaries on television and the ice cube detector. And along with these nuclear processes, muons are generated, and these have massive energy. They have 200 times the mass of an electron, and maybe 400 MeV in terms of electrical energy. They are massively energetic, and they move really fast. And one interesting thing about muons is if you're an educator, and if any of you are educators, you're probably aware of this. If you're not, then this is a great topic to bring into an A-level discussion with your students, or even if you're doing first year physics at teaching at university. Muon propagation through our atmosphere is a great example of time dilation, because Einstein predicted all of this, but of course wasn't observed in his lifetime. But from our perspective, the muon only lasts for 2.5 seconds, 2.2 microseconds, which isn't long enough for it to be generated and then detected at ground level. But because it's traveling so fast, essentially at the speed of light, although if you're a purist, it's not the speed of light, it's 99.999, then from its time reference, it has plenty of time to get from its point of generation to be detected at sea level, which is great, because we can build simple things to detect muons and count them. And I bought this last year. I think it might have been a lockdown project, but you can buy a kit of bits from China for £17, and it's basically a Geiger-Müller tube, giving a pulse for each event. So you can connect that up to pretty much anything that will count pulses. I use a Raspberry Pi, and you can count muons. But the sensitivity is very poor. There's about 1 muon event per minute per square centimeter. The problem is with these detectors, with the Geiger-Müller tube, and indeed with the scintillator, which we'll look at in a minute, they detect cosmic events, yes, but also background beta and gamma, and that's ubiquitous, largely from building materials, maybe from radon coming out the geology, depending where you are. And so it's not that useful if you happen to be wanted to do any astrophysics. And so the way in which we eliminate the beta and gamma radiation is by stacking, in this case, stacking GM tubes together. So that an event registered on all the tubes simultaneously. And remember, these particles are traveling at the speed of light. So when we say simultaneously, we mean simultaneously, fractions of picoseconds. Then it will not be background. It'll be cosmic in origin. And so we put them together, and I'll show you the geometry in a moment. But it does mean that our aperture is very small compared to this 1 event per minute per square centimeter. And here we can see we've got our Geiger-Müller tubes, and we can see we've got an effective aperture here, and where we would expect 4 counts per minute, because it's 4 square centimeters, or 4 cubic centimeters. But because of theta, because the aperture, we only count between 1 and 5 cosmic events over 5 minutes. So the sensitivity is very poor. And this is the setup I've got here that I built in lockdown. And so we've got three Geiger-Müller tubes, and where an event occurs on each of them, it gets counted as a cosmic event. We've got some electronics to generate the coincidence for us. And here we have some data from October last year, 1 day's worth of data. And you can see where each vertical line is 10 minutes, but we're counting very, very few. And I went on holiday and wasn't doing any development, and that was what happened between the 11th and 24th of September. David Hearn has been doing this work for ages, and he did manage to record an event which was 40 times over the background. That was some time ago. January last year. We've just started a STEM project because MIT were concerned that their physics students were very happy doing computer modeling, not very happy doing lab work, building stuff and interpreting results from stuff. So they came up with this detector, which uses a scintillator and a photomultiplier to detect cosmic muons. And there's a little Arduino single board computer there to count the event. The scintillator block is 25 cubic centimeters. So that's what, 5 times more than the Geiger-Müller tubes we had earlier. And we got a bit of, we have the silicon photomultipliers optically bonded so that we can have a far greater sensitivity to our cosmic radiation detection. And UCRA, I'm a director of UCRA as well, and we're now able to, we've been working with MIT and can supply kits and built units, and we're talking to UTCs, sixth form colleges, etc., because it's a great project for students to build if they wanted to teach some electronics and electronic debug, data visualization, coding with the Arduino, MicroPython, or C++ coding, data visualization, and a bit of astrophysics and cosmology thrown in as well. So it's a great model. It's a great teaching model for students. So we're hoping that we can use this in our STEM outreach. Okay, hydrogen line observation. We're now getting serious. Peter East built this antenna, and you can see it's relatively simple, and we've got 2 amplifiers and another of these SDR dongles, and that's all the hardware required. And what we're looking at here is a drift scan across the sky as the Earth rotates, and it's generating this peak as it swings through the one of the arms of our spiral galaxy. And he's got different models for data visualization here as well. Brian has got one of these in his garden. And yeah, you need a bit of space. If you have a small garden with high hedges, it's not really very good because your horizon's going to be quite low. But yeah, great fun doing hydrogen line detection. And this is some of his data with the galactic longitude noted. Somebody else has just started a project where they're going to build some dishes for radio astronomy. That's dear old Lawrence Newell. Pulsars. I'm moving on a bit now because I tend to waffle somewhat. I'm a bit aware of the time. Okay, pulsars. Very challenging from the amateur's perspective, however it is possible. And radio beam is channeled from the pulsar because of the powerful magnetic field, and the magnetic field is off axis compared to its rotation. And my little animation here, it always works, never lets me down. It's quite good, even on Zoom. So there we go. We get the idea that I'm sure some of you are far more familiar with pulsar observation than I am. But radio pulsar observation is a real challenge. As I mentioned earlier, the amount of signal you get is very small compared to the noise, and that's even more so with this kind of observation. But you can see the hardware is quite simple. We've got a low noise amplifier and a filter, a bit of gain, and an SDR running into a PC. And the really clever stuff here that Peter has written and designed is the data processing to extract from all the noise the pulsar data. And this is typical from Peter. We can see that we have masses of noise. You need a bit of imagination to know that there's anything there at all. But with constant sampling and overlaying and averaging and clever computational techniques, Peter is just a brilliant programmer. We can extract data from the noise that describes the characteristics of the pulsar. And as I mentioned earlier, there are professionals using Peter's algorithms for their observations. Right, fast radio bursts. Right, a new phenomena, and they're reasonably. They're extremely fast. The difficulty is you've got to be looking at exactly the right place at exactly the right time to capture one. And they have a phenomenal energy. As it says here in my fourth point, in a millisecond, same energy as 3 days emission from the sun. And the signal strength received on earthbound stations is about the same as 1,000th of what you would get if you put a mobile phone on the moon. Not very much. And there's at the moment there's no generally accepted single explanation of their origin, of their cause. However, there's a great observatory, and they contribute to the UK radio astronomy community quite a lot. They're always presenting their data, and I think, I might be wrong, but I think this may have been the first radio telescope in Germany, and it's now an industrial heritage site, and it's run entirely by amateur astronomers, independent researchers. And they run MSc courses with Bonn University. They have interns. They have collaboration with academic institutes across the world. And in fact, at our last meeting, there was a new collaboration set up between this group and Bath University Astrophysics, who are looking at fast gamma ray bursts. Yeah, this is at the very edge of what the independent researcher can achieve. And there we have it. I think this was their first observation, and they were extremely pleased. I think they might have just been lucky the first time. Since April, I think it was last year, they've been this has been their main research project, and they found some of these fast radio bursts. They stop, they pause, and then maybe weeks, days, months later, they come back again. Very mysterious, but extremely interesting. Okay, in conclusion, yes, we're getting there now. So. The independent researcher can do a lot with very little. It offers opportunity to develop electronics and coding skills if that's your interesting. We're active in citizen science and school STEM projects, and the Astronomical Association is very active with the BAA radio astronomy group. It all supporting the independent researcher, and it covers a much larger band of the EMR than visible light, and it complements our understanding of the cosmos. So we got there in the end. Thank you so much for your attention, and thank you for inviting me. I'm happy to answer any questions, although I don't guarantee any really sensible answers. Thank you.
Thank you very much for that. It was really interesting.
Brilliant. One of the chaps at the geologist lab does radio astronomy, and I must admit, I never really asked him what he did. But obviously there's an awful lot of different things you can do. That was fascinating. Thanks very much.
Oh, you're very welcome. Yeah, he probably does one or two of the things I've spoken about this evening, that is for sure.
Because I'm trying to think what it is John Gallagher does. He does the ham radio stuff, but he does radio stuff as well, because he gave a talk at the Society. Remember, and he brought his radio thing with him, his antenna with him, and he showed us how he hooked it all up and everything. And that was a long time ago. John's a member of our society, and he looks after the laptop and stuff. But
yeah, I would say more than half our members are radio amateurs, and a lot of those have come into ham radio from astronomy and radio astronomy, and the other half are radio astronomers that are ham radio have come the other way. They've started with ham radio and then found there's a strong crossover with radio astronomy. So yeah, there's a lot of migration. But I'm doing a presentation at the local ham radio club at the end of the month.
Aye, because he's in a group, you know, he's in one of the ham radio groups and that, you know, because he's had talks and that. You know. But it's really fascinating. So any questions for Paul?
I've got a quick one. Paul, yeah, a quick one. Has anyone managed occultation timing when the moon's gone past a source, or are the sources that are available too dim for amateur astronomers to get the signal from?
Yeah, that's a good question. I think the signal strength would be too small.
Yes.
Noise is a great problem, and very sophisticated electronics and cryogenics are used in the professional community, but you need some serious budget and engineering input to maintain that kind of kit.
Yes, I have got some observations from the 42-foot at Jodrell Bank.
Oh, yes.
When that went in front of the Crab pulsar. I pointed it out to Tim O'Brien, and I thought he was going to use a small student telescope, the 42-foot, to point at the Crab Nebula, but instead they pointed the Mark II at it. And they've got some nice traces of the occultation with some funny shapes.
Yeah,
and apparently they were using that on the graduate training course. I don't know if they still are.
May well be. There's a lot of student training at Hubble Bank with Manchester University.
Any other questions?
John?
John Davis.
Yeah,
Right.
so,
Hi.
hello.
Hi, John.
Paul, I don't go back to it, but early on in the slideshow, you showed 4 pictures of the Crab Nebula in X-ray, ultraviolet,
Yes.
visible and radio.
Yes.
Are they the same scale and orientation, or are they different scales and orientation? Because I got the impression that the last 2 were kind of offset by about 25 degrees or something. I have no idea about the top one, which was the X-ray.
Yeah,
picture.
I'll be honest. I don't know. I saw those slides and I thought that's a great illustration of the same object at different wavelengths.
Yeah, sure. I mean, I just wondered if they were all on the same scale, but you don't know. Fair enough. That's not important.
I can imagine there could easily be some rotational discrepancy between them.
Just thought you might have. I just thought you might know off the top of your head.
Yeah, no, I don't.
I've got a feeling, John, there's a movie somewhere that fades from one to the other. Possibly on one of the radio astronomy sites. If you search for Crab Nebula radio movie, that sort of thing, you might find something.
Okay. Yeah, may well be something on YouTube, actually.
I've got to say, as an infrared astronomer, I don't regard myself as being even slightly close to the radio, by the way. These people live in a completely different world.
Any other questions? I think it was such a comprehensive talk that people are just trying to take everything in, all the information in, and digest.
There was quite a lot there. I'm sorry about that, but I wanted to cover the whole gambit, as it were, and zip through it relatively quickly.
Because any time I do talks, you know, I've got some talks, but I mean, I put everything, I cram as much in as possible so that I don't get any questions at the end because of my foggy medicated brain, because I can't remember nothing.
Yeah.
I mean, that I cover everything, so people are just sitting there going, and then somebody will say, "Is there any questions?" And then they'll go, "No," and I'm going, "Thank goodness." But that was really interesting. So thank you very much for a fascinating look at radio astronomy. It's amazing the amount of data that can be achieved using relatively simple bits of kit that can help provide new and interesting information about the universe. I mean, and that the objects like the Crab Nebula and other galaxies and different things, it's just fascinating. Right, so I'd like us to thank Paul in the usual way.
Thank you very much. You're very kind.